Hello scholars, Mr. Hinkle here. Let's talk about the birth, the development, the life, the ending of stars. It's called stellar evolution, and that is what we are doing in this lecture. Our objective is to introduce stellar evolution and then talk about all the different phases in the life of a star. Okay, so quick definition, stellar evolution is the process by which a star changes over the course of its lifetime. It's got a birth, it's got a main sequence, it's got an old age, and then it dies. There is a theme here in the universe. A person like me is born, it grows up, it gets old. I will get old and I will die. The universe was born, it grows up. At some point, the fate of the universe, the big crunch, the big freeze, or the big rip, who knows? Solar systems have a beginning, a middle, and an end. So do stars. They're governed by nuclear physics, thermodynamics, and gravity, all things that are happening in the world. So it goes like this. We have stars because of the force of gravity. Stars exist because of gravity. And there's two forces. There's gravity and there's fusion. Gravity is pulling in and fusion is emitting out. So what is fusion? Well, fusion, I guess I skipped ahead. It's thermal nuclear energy, right? Stars are born in clouds of dust called a nebula. The nebular theory is the idea for how solar systems develop, but now we're focused in on just the star. So stars form through gravity in a solar nebula, where the nebula collapses underneath its own gravity, begins to form a protostar. It also forms planetesimals and planets, but that's not this lecture. That's nebular theory. The protostar heats, not hats. It heats to the point where nuclear fusion begins. And this is what I was talking about. Thermal nuclear energy begins nuclear fusion. And nuclear fusion is a nuclear reaction where two or more nuclei are forced together and combine, creating a new, larger atom, producing solar radiation. So essentially, you have hydrogen becoming forced together and fusing to become helium. Hydrogen to helium. And the byproduct of this is solar radiation. What force combines two hydrogens? What is it? Gravity. The gravity is so strong that it, boom, fuses two hydrogens together. Now, helium is formed because the periodic table of the elements is defined by the amount of protons in the nucleus. So when we go from one proton to two protons, we now have helium, and the result is solar radiation, or light from the sun. This is the birth of a star. The gravity is so strong it forces two hydrogens and turns it into helium, and boom, bang, pow, we have solar radiation. Okay, so now that we understand the force of fusion, our star has been born. A star is born, like our star, and it's giving off light. Well, that light that it emits, it becomes stable between the amount of fusion and gravity. Our sun is about 4.6 billion years old. It's how old the solar system is. It's how old Earth is. The universe is 13.8. And it's stable. It's in the main sequence star stage, and it's stable about halfway through its life. Our sun will live about 10 billion years, so about another 5 billion years. That's based on its size and its luminosity and the amount of solar radiation that it's emitting. Fancy calculations have been created. So there's a lot in this figure that says we're about halfway through our existence in the solar system. Yellow stars are main sequence stars. They're of medium size. We call, yeah, like I say, we call them main sequence. Stars can continue to grow and become late stage. Is that what I have up here? Post main sequence, also late stage. They can grow into what are called red giants. They can continue to grow into what are called supergiants. So this is when the hydrogen in the core is exhausted, the fusion stops, the core contracts and heats up, but the outer layers expand and cool. So it's past its stability, the star is past its stability, and it's in the later stages of its life. And now, because of all of these things that I've highlighted here, the star expands a little bit, red giant, or a lot, supergiant. Okay, what comes next? Well, after the late stage is the death of a star. And depending on how big that star has grown, a few different things can happen. Low mass stars turn into what is called a white dwarf, and it's small solar system body, and then it will be surrounded by a solar nebula, and that nebula will then be the nursery for the next star to form. Stars can kind of recycle. Or if it is a red giant or a supergiant, the core might collapse on itself, and the result of that is an explosion called a supernova. A supernova explosion from the core collapsing. But what that leads to is either a neutron star or a black hole. The difference here is black holes have gravity so strong that the light cannot escape them, and so when we see them through the telescopes, they actually look like a black hole. Neutron stars are incredibly dense objects, also from the collapse of massive stars, supernova explosions, but we can actually see them when we look at them through the telescope. So temperature on the x-axis, luminosity on the y-axis, and actually following the pathway of stellar evolution. This is a Hertzsprung-Russell diagram, or HR diagram. Here we have stars that are being born. This is the main sequence. They might phase out and become, right, for small mass stars, phase out and come right back down into white dwarfs with solar nebulas. The star might expand into a giant, a red giant, or a supergiant. These are the stars that at their fate are going to explode and become either a neutron star or a black hole. So different pathways for different stars. Their course is not set. Who knows what life will bring them in their old age? Stars have a life, they have a birth, they have a death, and it is defined here in the process called stellar evolution. We observe the various stages of what's happening through telescopes. This is how we know so much about what's going on in the universe, about astronomy, about cosmology, because we have very strong telescopes, and we look at these information and we develop theoretical models with quantum mechanics and relativity, and we put it all together to give us an idea of how our universe works. Thank you so much, and I'll see you again.